he said, this is Forklifting Django. So quick intro, as he said, my name is Noah. I work for a company called RIDECTL that does transportation software, and I do a lot of stuff in the, is that working okay? Yeah, in the ops and Python worlds. So web deployment is hard. There's a lot of different steps that have to happen. They all have to happen in exactly the right order. They have to happen over and over. It has to be fast, it has to be easy to use. All of these put together, very hard problem. In the beginning, web deployment was basically a manual process. We'd all just SSH some servers and run some commands. Works, but it's very slow, it's very time consuming, and it's very error prone. So over the last 5 or 10 years, there have been a lot of new tools, things like Fabric, Chef, Ansible. They all help to automate the process, making it more repeatable, less error prone. New tools like Docker came into the fray to help move more tasks from deploy time to build time. But with all these new tools came new challenges. So let's set the stage. My main web application for work. This is an actual case study. I'm not making this up. This is our real thing. It's called Summon Platform. It is unfortunately still in Python 2, so this is a Django. Although for deployment, Django 1 versus Django 2 doesn't really matter all that much. But we've got Celery for backends and Django channels for WebSockets. We're running Postgres as our main database. We've got Redis as a cache, and we've got RabbitMQ as the backend for Celery. So a fairly standard, big, monolithic Django app. One slight wrinkle is that we are single tenant, so we deploy a separate instance of the application for every one of our customers. We're a B2B app, so we have a small number of very big customers, and we really want to allow for things like independent versioning. We can upgrade each customer individually, and we want to be really sure that customers can't see each other's data, and one easy way to do that is they're just not running on the same platform. But even with a multi-tenant deploy, as most people are doing for more standard applications, the same problems apply just at a smaller scale. So, what did the deployment system look like when I started this adventure? We were AWS based, we still are. We were using GCP for a few things in experiment, but AWS is what it is. We primarily use Terraform for provisioning the actual infrastructure, things like setting up the EC2 instances, RDS, all that kind of stuff. We have some side Python scripts for things that we can't do in Terraform. Same general idea. And then Ansible for configuring the systems and deploying the actual application code using Git. Secrets lived in Ansible Vault, and access control for deployment was managed by who had SSH access to the server at all. Solid setup, probably a thing that a lot of people have worked with in the past, but launching a new instance took a couple hours, and it had to be done by my team because it required access to things like AWS. We didn't want to give that out to every team. Similarly, scaling up and down, we do car sharing and ride sharing, so they're highly time variant, and we weren't really built for auto scaling, so we had to run for peak demand, which meant we had a lot of idle computers sitting around a lot of the time. We also had a bunch of Django-based microservices, but let's just focus on the big application for now because it's more interesting. We did have a few constraints for the new system. We knew we wanted to use Kubernetes. It was already in use before I joined the company for some of their microservice experiments. And I came in as a Kubernetes person. It's my weapon of choice for container wrangling. We knew we wanted to keep using RDS and Cloud AMQP for Postgres and RabbitMQ respectively. I'm more in favor of most than running databases on Kubernetes. I actually think it's not a terrible idea, but I do work at a startup with a very small team, and if I can exchange money for not having to manage databases, I will do that every single time. Also, leaving the existing databases exactly where they are makes migration a lot easier because we can just move the web servers over and leave it at that. What do I mean by forklift migration? While I can make some changes to the backend app, I have a very close working relationship with our backend engineering team, the goal was to not have to drastically rebuild the applications. We wanted to just pick it up from where it was in AWS and slide it straight into Kubernetes. So all that laid out, I was ready to roll up my sleeves and jump on in. First step in containerizing any application is to build a Docker container image. Multi-stage builds are especially useful for this. As you can see, the as build up there somewhere. It's a really big screen. Using multi-stage builds means that you can have separate build requirements and runtime requirements. Especially for Python applications, the build requirements are often very, very much bigger than the runtime requirements. One thing of note here is that I am not using a virtual env. I know some people in the container world disagree with me, but I haven't found them very useful, and it keeps things nice and streamlined. The container's only ever going to be used for one thing anyway, so why do we need virtual envs? So after the build phase, we set up the smaller runtime image, and we copy over just the needed files. Also sets up a non-root user to run your application as. A lot of people forget to add this when they're containerizing applications. Running as root inside a container is not as dangerous as running as root outside a container, but it's still not a good idea. So my first attempt to getting things set up in Kubernetes was purely static manifests. No automation beyond just running kubectl apply. How many people here have used Kubernetes before? Show of hands. Not a ton. OK, so I don't have slides for this, but I'm going to try to ad-lib a quick introduction to Kubernetes. So some terms. Pod is basically the Kubernetes word for container. Technically, a pod can contain multiple containers, but in this context, really all we care about is one container at a time. So anytime I say pod, just think container. Kubernetes also uses these YAML files. It has you can see here, this is a container definition. So this is one container within the pod. It specifies the image, the command to run, what ports to expose, and the resources required to run it, and then some volume mount stuff, which we don't need to talk about right now. So anyway, so this was a very simple static definition of running a single container, running my migrations, and then running Unicorn. A quick improvement to this was to move the migrations up to what's called an initContainer in Kubernetes, which is just a container that runs before your run forever daemon pod, or your daemon containers. And I also was experimenting at this point with how much dynamic configuration can I do? Can I make the Postgres password in the configuration file be dynamic? So using an initContainer and sed, the lovely trusty command line tool, to rewrite my config YAML on the fly. This helped with a lot of issues in making things more dynamic, but we had a lot of issues with ordering. So if we ran multiple replicas, we ran multiple copies of our application pod, of our application container, they would all try to run the migrations, which is usually not what you want. You want to run them once and then be done. Similarly, because the migrations were sort of embedded into the running of Unicorn, other things than Unicorn, like Celery and the channel workers system, they would come up before the migrations had run. It's provided a good start, but clearly we need a more organized deployment system underneath this. A few things I glossed over, just so we're keeping track of them. I showed you running Unicorn, but running Celery, Daphne, and channel workers is very similar to the structure I had before. Just instead of running Unicorn, you run the other daemon. I'm ignoring Celery. We'll get to that one in a little bit. Also, my application is mostly an API that's used by mobile apps. So the web interface is pretty much only used by the administrative staff at our customers. So we decided to build all of the static files into the image and serve them using a cut down version of a tool called Caddy, which is a nice, simple all-in-one web server. This means that we don't get the benefits of, say, like a full CDN structure using S3 as the origin, but we don't care if it's slightly slower. All of the HTTP traffic for Unicorn and Daphne and the web services would go through the Kubernetes ingress system. So that handles HTTP routing within Kubernetes automatically. And the other thing that I started playing around with in the sort of first phase of this was using the Postgres operator from Zalando, which helps automatically provisioning Postgres databases. Like I said, we wanted to use RDS in the end, but RDS is very slow. It takes 20 minutes to set up a new database, and that wasn't really conducive to rapid iteration and testing. So we did switch to local Postgres for a little while. So by this point, I had a working proof of concept. I could deploy an application on Kubernetes, but it wasn't really reliable and it wasn't really repeatable, so we had to move on to another solution. Next tool in the standard Kubernetes quiver is a tool called Helm. It's billed as the Kubernetes Package Manager. This is overall very similar to what we had before. I can just take those manifests, I can make them into little templated versions of themselves, put them in a Helm chart, and I can rubber stamp them out as many times as I need. So that gave me repeatability. I'm not going to go over the chart itself. It's basically exactly the same manifests as we saw before, and they don't really fit on slides very well. But like I said, it made the repeatability way better. We could do this as many times as we wanted, over and over. And we could version the chart as necessary, as opposed to static manifests where it was just sort of loose files in Git, so we didn't know what versions of things we were doing where. Helm is also great because it's widely supported by a lot of tools in the Kubernetes ecosystem. We had a lot of experience working with it on other projects, but it wasn't all great. It did fix some things, but it brought a lot of new. Notably, it did not help at all with sequencing and ordering. It does have a hook system that we tried to use for a while, which lets you sort of do minute levels of ordering and sequencing control, but the error handling wasn't great, and overall, we just decided it was too complex to work with. And there's also some major gaps in the Helm ecosystem. It doesn't really have a testing system. There's a really, really basic thing called Helm Test built in, but they don't really give on how to test your applications. Also, secrets management, coming from Ansible, we had Ansible Vault available. Helm just kind of says, not our problem, and defers secrets management out to the plugins ecosystem. And then the big problem, Tiller. It's the server-side component of Helm. It's the piece of Helm that interacts with the Kubernetes API, and to put it lightly, it's a security nightmare. They're already removing it in Helm 3. They've actually already removed it in Helm 3, the next major version, but that's still at best months away, possibly another year. So we had to figure out another set of workarounds. Very broadly speaking, the issue with Tiller is that you need to give it admin level access to your cluster so that it can take all the action on your behalf, but Tiller does not have any internal access control or authorization framework, so anyone with access to Tiller automatically gets full admin. So it worked, wasn't as smooth as the experience we wanted, and Tiller, because of the security problems, made a self-service option, let's say tricky to set up at best. So with that, our current approach, hopefully the final approach, a Kubernetes operator. Operators tie together three main concepts in Kubernetes: CRDs, watches, and controllers. A custom resource definition, or CRD, is a way to add new object types into Kubernetes. So just like pods that I mentioned before, or services, or ingresses, or all those are Kubernetes types, but we can add our own types that will work the same way. In this case, we are creating a type called summon platform that will hold all of the configuration options related to deploying one instance of our main web app. And then I can use it just like I do any other Kubernetes object. Again, if you're not familiar with Kubernetes, don't worry. The important thing to here is to see under spec, I have a version of my application that I want to deploy, and I have some config. In this case, I'm just setting the Django debug flag. It's a little bit more verbose than a Helm values file, but it allows for things like schema validation. So I can say like version must be a string and it must match this regex. And it allows idempotent application via kubectl apply. CRDs give us a place to put the configuration data itself, but then we need to actually do something with it. And the heart of this is something called an API watch. It's kind of like a push notification for the Kubernetes API. So whenever any instance of one of my objects changes, I can set it up so that my code gets a notification and can do something with that change. The heart of any operator is a controller. Each controller sets up some API watches, waits for a change, and then does its best to make sure that the state of the world reflects whatever that change wanted to do, and then repeat that in a loop forever. So you can have a lot of different weird controllers, but almost all of them will follow this pattern. There'll be some kind of root object, in this case summon platform. It sets up an API watch to watch for any changes in any of those root objects. When it gets a change, it reads in that root object, it generates a whole bunch of Kubernetes data, in this case some deployments and services and ingresses, and then it basically calls kubectl apply to apply that state to the universe. So we're effectively rebuilding the state of the universe every time any change happens in any summon platform object. This helps to ensure that we don't get drift over time, and that each controller is responsible for only one type at a time. But okay, enough about the ideas of the system. Where's the code? Unfortunately, writing complex operators in Python is currently doable, but a bit tricky. There's two projects that are trying to make it easier to write operators in Python, one called Kopf from Zalando and another called MetaController from Google. They're both looking relatively solid, but they're aimed at relatively simple use cases, and they're early on in development. So you could also go with the straight, like, raw Python API client library, which does exist for Kubernetes, but you'd have to rebuild all of the controller loop stuff that I mentioned before from scratch. That's not easy. So in the end, we decided to stick with the more community standard kubuilder and controller runtime stack, even though those are written in Go. As such, I will be translating some of my code samples into pseudo Python for you. Please don't try to run them directly because they're just examples. I'll mention it later, but all of my code is open source. And if you want to go read my terrible Go, you can go read my terrible Go. So first problem that we tackled was iteration from the Helm iteration was sequencing. We added a lightweight state machine to this, so we could sort of figure out how far along in the process we are in provisioning. The first phase, initialization, covered setting up databases, then running the migrations, then deploying, and then becoming ready. Or hopefully there's no errors, but never know. So this is one of these converted pieces. This is how we handle migrations. So because a controller is real code, we can write code that is specific to understanding Django migrations, whereas Helm is a declarative system, and you just sort of have to run with what they offer. The general idea here is we store what version of migrations we have last successfully run in the status of our custom object. So if we get triggered and there has been a change, we can check to see if the current version matches the previous version, then we're all good. We've already run the migrations, don't try running them again. Otherwise, try seeing if there is currently a running migrations object. If it's not found, that means that this is a new deployment and we want to start the migrations. If it was found and the status is success, that means we had already started them, they have succeeded, so record that we ran the migrations and then say we're done. Otherwise, they're still currently running and it was some unrelated change. So this allows us to have very, very careful control over the exact ordering. We will not start deploying any new web or Celery code until the migrations have already completed. I put aside Celery Beat earlier, so now we have to talk about that again. There's two problems with Celery Beat. Celery Beat is a great tool. It's kind of like a replacement for cron almost within Celery. It lets you do scheduled Celery tasks. But two things. One, you can only run one copy of it. If you run multiple copies of Celery Beat, they will all run independently. So if you run 2 copies, you get 2 copies of every scheduled task. Not usually what you want. Look, my slides advanced. The second is that it's stateful. It has to store the last time that each scheduled task has run so that it knows when to run them again. By default, it does that in a local file on the file system. There is a tool called Django Celery Beat, which moves the state storage into the Django database, but depending on how many scheduled tasks you have and how frequently they run, that can be a lot of load onto your SQL database. So there's a project called Celery BeatX, which fixes both of these. It adds a simple master election so that they can have multiple copies running, but only one is active at a given time. And it moves the state storage into either Redis or Memcache, which is generally a much better fit for that kind of use case. There is a but, though. It is Python 3 only, which hopefully for most people that are not me, that's not an issue, and you can just use this and be happy. But I didn't have that option. So instead, I had to use a thing in Kubernetes called a stateful set. Stateful sets are like deployments, just like we saw before with running Unicorn, but they have a couple of extra features. One is that they directly integrate with the persistent volume provisioning layer in Kubernetes, that we could have a place to put our persistent storage. And the other is that they make very, very certain that you only ever have one running, which in this case is important. We do some of our billing stuff through scheduled tasks, and if we have duplicate tasks, we run the risk in certain cases of double billing. That's bad. So we've got Celery Beat, we've got our ordering. Next up was to figure out a better way to handle databases. So I mentioned before we were trying out a thing called Postgres Operator, which is another operator from another company that manages Postgres locally, but we wanted to move this into RDS. So we used the same approach of writing a custom controller, writing a custom type, writing that control loop, but for databases. So in this case, we have a CRD called Postgres Database. It has a name. It has which extensions you want to imply, because we're using PostGIS. I'm not going to show the rabbit one because it doesn't fit as well on a slide. But the general idea is that this automatically creates a database, automatically creates a user, sets a random password. Come on. And then you can take those random credentials and you can work them in. So before I was using sed, now again we have real code running in the operator so we can make it more fully dynamic within the operator itself. So we can watch the secrets that contain the randomly generated passwords. We can build out a Django config. We can serialize that to YAML because we reuse a YAML file and read it in our settings.py. And then we bake out that YAML back to a secret. This means that the application doesn't need to understand any of the dynamic stuff happening behind the scenes. All it sees is, I got a YAML file, I'm happy. This is part of the whole idea of a forklift migration, that we're handling all of the Kubernetes dynamic magic completely internally within the operator. So put it all together, and we have a new end-to-end workflow. I haven't mentioned Argo before because I'm running out of time, but basically just watches a Git repository full of Kubernetes stuff and syncs it into the Kubernetes API. So we have a GitHub repo full of files, one YAML file for every instance of our application. Somebody makes a pull request, they want to deploy a new version, they go into the YAML file for that instance, they edit the YAML for the version field, they make a pull request, they get it approved, they merge to master. When they merge to master, Argo CD wakes up, it sees that there's been a change in Git, it synchronizes that into Kubernetes. Second piece of the puzzle I can mention real quickly, again, because running a bit low on time, RIDECTL. We wanted to try to make things a little bit easier. Kubernetes can be a little bit hard to use for people that haven't worked with it before. So we wrote a very simple command line tool. It doesn't do a whole lot. The shell and PyShell commands are wrappers around kubectl exec, which lets you run a remote shell in a running container somewhere in Kubernetes. All it does is connect to Kubernetes, figure out which pod to talk to using the sort of pretty name. It gets the long, complicated Kubernetes name and connects you into either Bash or into a Django managed.py shell. Similarly, DB shell, it just connects to the Kubernetes API, figures out what database you're supposed to connect to, and runs pSQL to connect you. kops on AWS because we wanted to be physically close to RDS for lower latency. We're using kops with CoreOS. So. Any other questions?
Have you tried cronjob for Kubernetes instead of writing from that?
Yep. So the question was, have I tried using the cron job type within Kubernetes instead of using celery beat? We have. The problem is, like I said, forklift migration. So that could be an option in the future, but we didn't want to have to rewrite all of that code. We would have had to make a management command way to kick off the job code as it existed, and then sort of piece it into the system. Also, the cron job system isn't so great for things that have to run every, say, 60 seconds. There is some overhead in launching the container and loading up Python and all that stuff. So that works great if you have something that runs every 5 minutes maybe, but at every 30 to 60 seconds, the overhead's going to be a bit of a problem, and we didn't want to have to rewrite anything.